Hi, this is the last lecture in the course of Introduction to Physics, and today we have to conclude the topic we started last time, that is geometrical optics. I will just remind you that we considered a lens. This is a convex lens, and in optical schemes, on the sketches of optical schemes, such an optical device is indicated by this symbol, like double arrow. So this is a convex lens. And also we considered a concave lens, which is indicated on the sketches of optical schemes in this way. This is a concave lens. Also, we discussed the lens formula. The lens formula is connecting the distance from an object to the center of the lens, A, and the distance from the lens to the image. So this is the object, and this is the object image. And these two distances are somehow related to the focal distance. And the formula is very simple. It's 1 over f equals 1 over a plus 1 over b. Let us try to find b from this formula. So 1 over b will be equal to 1 over f minus 1 over a. And in this way, b will be fa divided by a minus f. So this is the distance from the lens to the image of an object if an object is located at the distance a from the lens. And this formula gives you much information. For example, if a is larger than f, then the denominator of this formula will be positive and b will be also positive. B is positive quantity. Positive means that the object, the image formed by the lens is located somewhere to the opposite side of the object. Then it's also obvious that if a equals focal distance, then there will be a 0 in denominator, and the whole formula will give you an infinite value for b. In this case, b tends to infinity. What does it mean? It means that if the object is placed at the lens focus, then the image will go to infinity and will be somewhere at the infinite distance. Actually, such an image cannot be observed. And also there is another situation if a is less than f. If a, the distance from the object to the lens, is less than focal distance, then the denominator will be negative and the b will be negative. In this case, the b is negative. What does it mean the distance b is negative? It means that the distance b should be directed in the opposite way, and the image of such an object will be located somewhere to the left side of the lens in our sketch. So this is a very interesting situation, and I will try to show it in greater detail on a separate sketch. So we consider the situation when A, the distance from the object to the lens, is smaller than focal distance. So we have a lens, the principal axis, which goes through the lens center optical pole, and here is the focal distance of the lens, and the object is located somewhere at the distance which is less than the focal distance. How can we obtain an image of such an object? So the rays of light which go in every direction will be refracted by the lens, and in order to find the result of this refraction, I choose several rays, at least two. I need two rays at least. So I will take this ray which will go unreflected, unrefracted, and also I will choose another ray which will go parallel to the principal axis, and this ray must be deflected to the focal point. And so if we put an eye, a human eye here, what will a human see? We will see the rays which go in this direction and the rays which go in this direction. We will see somewhat diverging rays. Also there are many rays in between. Many rays in between, and also here. We only draw some a few rays, two rays. We can draw another ray, for example, the one which will go from the focus, and it will go then parallel. But we see here a bunch of rays diverging, and when a human eye, or a glass of any tube or any optical device, or a human eye looks into such an optical field with diverging rays, the human eye will perceive an object somewhere at the point of intersection of these rays. So an object which we will see if we stand here and look through the lens, we will see an object located at this point, at the intersection of all the rays. All the divergent rays will be focused by the human eye, and we will perceive the image as if standing here. Actually, there is no object here. The object is located at this point, but the image of this object will seem to be located here. And what is the difference between the image with negative b? I remind you that b is the distance from the lens to the image, and if b is to the same side of the lens with a and b are to the same size, then b is negative in this case. If b is negative, then this image is, well, it's very strange. It differs much from the real image which we obtained here. What is the difference? The difference is simple. If we put a screen here in this place, if we put a white screen, then all the rays converging to this point and forming the image will be scattered by the white screen, will be scattered in all the directions. And if we look at this screen, we will see this object. We will see the image of the object on the screen, a distinct image on the screen, because every point of this screen will scatter the light rays coming here. And so we will see the image on the screen. That is the principle of projecting pictures on a screen. Like in cinema, if you go to see a movie, you will see just exactly this principle. Every point of the white screen is scattering the light rays which come here, and if the light rays are focused on the screen, then you will see the distinct image on the screen. So if we have a positive b, positive distance of an image from the lens, then you can see this image by putting a white screen here. But if you see a negative b, negative distance from the lens to the image, then even if you put here a white screen, you will see nothing, because actually the rays do not converge here. They go from this point, and it seems to us that the diverging rays are coming from this point. It seems to us, but actually if we come here, we will find no rays. No rays exist in this part of the space. And so if we put a screen here, we will see nothing. That means that this image with negative b differs much from this image when b is positive. That is the real image, and that is a virtual image. So here we have a real image, and here we have a virtual image. What is particular about virtual image, apart from the fact that it cannot be seen on a white screen? There is another very interesting property of this image. The dimension or the height of this image, virtual image, is larger than the height of it may be larger than the height of the object. And it means that when we look at the object through the lens, we will see a larger image, a larger, as if magnified object. And so this is the principle of work of magnifying glass. When you look at some small object through the magnifying glass, you can see that the object is magnified. It's increased in dimensions. But you will see the virtual image of the object. Also, it's possible to arrange a larger size of a real image, but it will be on the screen. It will not be formed in the human eye. We could see the screen from some distance, but in this case, the image is actually formed in the eye after the human eye focuses the diverging rays onto the retina in the human eye. So in this case, the real image is constructed inside the human eye on its retina, because we see the divergent beam of rays, and all these divergent beams, all these divergent rays seem to come from a single point which we perceive as an image, but this is actually not a real image, because if we put a screen here, we will see nothing. We can only see this image through the lens, and the screen will not help us in this case. So there is a distinct difference between real images and virtual images. Talking about lenses, one should mention that sometimes the power of the lens is measured in certain physical units. So we know that some lenses are powerful and more powerful, some lenses are less powerful, and that depends on how what is the magnification of this lens. So the power of the lens is usually described by such a quantity which is equal to 1 over f, and this is called the power of the lens, and this quantity is measured in dioptries. So this is measured in dioptries or dioptries, whatever pronunciation you prefer. In dioptries. So if we say, for example, that we have a lens with the power of 5 dioptries, what does it mean in the international system? 5 dioptries will mean that the focus equals 20 centimeters, because 1 meter divided by 20 centimeters will give you 5. 1 meter divided by 0.2 meters will give you 5. 5 dioptries. This is actually a dimensionless quantity, which has the name of dioptries, but the dimension is, the dimension is, yes, in many cases the dimension will be just 1 over meter. 1 over meter. So you may find lenses, more powerful lenses. The more dioptries is in the lens, the more powerful is the lens, and the smaller will be the focal distance. If the focal distance is very large, it means that the lens is very thin and very weak, and the power of this lens is very small. So after this small remark, we go to a next subtopic, which will be a spherical mirror. I will draw a spherical mirror which has its center, which called the pole, and if we draw a line through the pole perpendicular to the plane of the mirror, then we will have a principal optical axis of the mirror. And the mirror will have also some radius of curvature. So this will be the radius of curvature of the mirror. And that point will be the center of the sphere, of this spherical surface. So what we see on this sketch is a concave mirror. It's a concave mirror. A concave mirror. Certainly there are convex mirrors. Well, you can easily imagine a convex mirror, something like that, which will have a radius of curvature here, and the reflecting surface will reflect light which comes from this side. And in concave mirror, the reflecting surface is concave. It reflects light that comes from the left side in this sketch. So what happens in concave mirror, how images are formed? Let's consider the formation of image. We choose some point and we imagine that this point is radiating. This is a light source. It's radiating light in different directions. And we choose only one direction at first. We choose only one ray of light which goes to a certain point, which has already been indicated on this sketch. And this light will come into this small surface, which can be considered small flat area, which is directed along the tangent line to the concave mirror. And the tangent line is perpendicular to the radius of curvature in this, drawn to this point. And so if the light ray goes this way, then it will fall on a small flat area. And the laws of reflection will work in this case, so that the angle of incidence will be equal to the angle of reflection. Angle I will be equal to I prime, for example. Angle of incidence must be equal to the angle of reflection, because the light ray encounters here a small, almost flat surface which is reflecting this light, and so the laws of reflection work here. Angle of incidence equals the angle of reflection, and so the light which was emitted at this point and which went along this light ray returned later to this point. So if this is the source of light, then this will be the image of the source, and I will denote the image as S prime. Another ray which goes from this source of light, and there are, I repeat, many rays going in different directions. Another ray may be considered as going along the principal axis, and this ray will go here and it will be reflected backward, and it will also come to point S prime. So we have two rays, at least two, one going along the principal axis and reflecting here, and another ray going along this path, and these two rays will intersect at the point of S prime. So this point will be the image of the point S, which is the source of light. Let's denote angles. This angle will be, say, gamma, and this angle, well, let it be alpha, and this angle, let it be, it's a different angle, let it be gamma prime. Angle gamma characterizes the position of the source of light, and angle gamma prime characterizes the position of the image of point S. Also, we may introduce for consideration the height at which the height of the point at which the ray is reflected from the mirror, the height above the principal axis. I remind you that in all these situations we consider so-called paraxial rays. Paraxial rays means that we consider only the rays which are close to the principal axis, the rays located not far away from the principal axis. If we consider rays that go far from the center of the mirror, if we consider rays that go somewhere at the edge of the mirror, then the optics will be more complicated, and the formulas will be more complicated, and the image formation will be more complicated. So as a first step, we consider the simplest situation, and the simplest case is just a paraxial rays which are located closer to the, which go propagate close to the principal axis, so that h is small. H is smaller, much smaller than the radius of curvature. It's not like on my sketch. I have drawn a sketch especially in such a way as we can see anything. We can see something here on this sketch. But actually we should remember that this h is much smaller than the radius of curvature. And it means that this distance is very small and it's negligible, and we will neglect this distance in the case of lens. And also we have another distance here, which is radius of curvature, as this point C is the center of the spherical mirror. So what can we say immediately about this situation? We can say that the angle of incidence I must be equal to the angle of reflection I prime. That's the law of reflection of light from a small flat surface here. Also, we can say that in any triangle, I will draw any triangle, arbitrary triangle, and that will be angle gamma, and that will be angle A, and that will be angle B. So in any triangle, A plus B equals gamma. So this is the relationship between the angles, internal angles in a triangle, and an external angle, which is shown here. This is the simple geometrical fact which can easily be proved if you draw a line parallel to the side AB, and then this angle will be equal to this one, and this angle will be equal to this one. So the sum of these two angles is gamma, which is written here. We'll use this property of triangles, and based on this property we can write that gamma, angle gamma plus angle I equals alpha. And the same thing will be true for another triangle, and we will write that gamma prime equals alpha plus I prime. Based on these relations, we can make some important conclusions. For example, if I add the last two equations, I will receive this thing. Gamma plus gamma prime plus I, gamma plus I plus gamma prime, will be equal to 2 alpha plus I prime. But we know that I equals I prime, so these two terms will cancel. And we obtain at gamma plus gamma prime equals 2 alpha. That's an interesting relationship between different angles here. Angle gamma, the angle which characterizes the source, and the angle gamma prime, which characterizes the position of the image of the source, and angle alpha, which characterizes the center of the spherical mirror. We have such a relationship. Also, we will use the relationship. We know that we consider only paraxial rays, and in this case H, this section H is much smaller than R. Therefore, for any angle, for example alpha, all these angles are small angles, and for small angles we know that sine alpha is approximately equal to alpha. That is true for small angles, and we consider only small angles because we consider paraxial optics, paraxial rays in this case. And that means that instead of angles we can use sine of each angle, because angle approximately equals the sine of this angle. So from this equation we can obtain that sine gamma plus sine gamma prime equals sine of 2 alpha. And now what is sine in this case? For example, what is sine gamma? The sine of gamma will be the height, the opposite leg in this triangle, divided by this distance. But for small angles, also another thing is true, that sine alpha for small angle, for small alpha, approximately equals the tangent of alpha. So in order to calculate the sine, I can take the length of this leg divided by this hypotenuse, or I can take this length divided by another leg, another catet in this right triangle, because for small angles this is the same. So I will use this approximation, and therefore I will find that sine gamma is approximately equal to h divided by the distance a of the source of light from the mirror. Again, I remind you that we neglect this small distance here because it's very small, because we consider only paraxial rays. Also, sine gamma prime will be equal to h divided by the distance b of the image from the mirror. And also sine of alpha, this is certainly 2 sine of alpha for small angles, and this will be 2 h divided by the radius of curvature, 2h divided by radius of curvature. That's an approximate formula which holds very well for paraxial rays. For paraxial rays, approximation works well. It's good approximation, but only for paraxial rays, only for paraxial optics. In this equation, we can cancel h and obtain the formula which describes the concave mirror. 1 over a plus 1 over b, that is the inverse distance of the source of light from the mirror, and that is inverse distance of the image of this source of light from the mirror, equals 2 divided by r. R is the radius of curvature of concave mirror. Now imagine that distance a can be taken anywhere. The source can be put at any distance a, even at very large distance. And so if a goes to infinity, then the source will be at infinity, and then actually parallel beam of rays will come here to the mirror from infinity. And if a is infinite, then the first term here will be equal to 0 plus 1 over b. And we know that if we have a parallel beam of rays, a parallel rays, a flat wave, actually, a flat wave coming and falling on the mirror, then all the rays should focus in a focal point, of this mirror. So in this case, we obtain that 2 over r is here, but actually the distance of the source from the mirror must be equal the focal length, because all the rays come here from an infinite distance. And infinite distance means that all the rays are parallel, coming here actually parallel. And parallel rays must be focused in a focal point of the mirror. So in this particular case, when a is infinite and the first term is 0, in this particular case, b must be equal to focal distance of this mirror. And from here, we immediately obtain that the focal distance, I will put it here, the focal distance equals r divided by 2. That is, the focal distance of the concave mirror equals to half its radius. So if this radius, the focus will be at the middle of this section. So this will be a focus, this point, the middle of this section, which equals radius of curvature. That's an important point, an important thing, that focal distance of concave mirror equals half its radius of curvature. If we take this into account, then we obtain from this formula immediately the formula for the concave mirror, which will look exactly like the formula for the lens. So that will be 1 over f. If f is equal to r over 2, then from here we obtain that this is just 1 over f. And the formula of concave mirror is exactly the same as the formula for the convex lens. Actually, a formula for concave lens is the same, but there are some details that should be pointed out for concave lens. We will consider it just a few minutes later. So this formula describes the formation of an image which is placed at distance b from the mirror if we know where the source of light is. If the source is placed at distance a from the mirror, then the image of this source formed by the mirror will be found at distance b from the mirror. And all these two quantities will be related with the focal distance of this mirror. And focal distance is defined by half the radius of curvature of the flat mirror. So we have already discussed that in the convex mirror, the b distance, convex lens, the b distance from the lens to the image can be negative. So other quantities can also be negative in some particular cases. For example, if you take a concave lens, then you will also have two focal points which are characterized by the fact that the parallel beam of light, a parallel rays coming to the concave lens, will go out of the lens as a diverging beams of light, and they will look as if they originate from the focus of this lens. That will be the picture. And in this case, the lens formula also works, but the focal distance must be considered as negative. For a concave lens, which is a dispersive instrument which makes the parallel beam of light diverging, for such an instrument, the focal distance must be considered negative in order to use the lens formula. So the next step which we will consider will be a few words about image formation in mirrors. We have already obtained the mirror formula, the formula which describes the image formation in the concave mirror. So if we have a concave mirror with principal axis and with focal point somewhere here, we know that this is half the radius of curvature, and we have some object, then what will be the rules of geometric formation or construction of image? Again, we remember that each point of the object radiates light in all possible directions, and we choose the direction which is convenient for us, convenient for consideration of this problem. We choose the one ray which goes parallel to the principal axis, and we know that the parallel beam of light will be reflected to the focal point and will go through the focal point. Also, we know that if we choose the ray which goes through the focal point, which comes through the focal point here, then such a beam, such a ray will be reflected parallel to the principal axis. So parallel ray is reflected to the focal point, and if we invert this ray in time, if we consider time inversion for this ray, then any ray which goes from the focal point will be reflected as parallel ray. We can use this simple property to find the point of intersection of all the rays. One ray goes here and another ray goes another path, and their point of intersection is here, and so that will be the image of the object. That is the object, and that is the image of the object. Such is one of the possible ways, one of the possible methods of constructing images formed by concave mirror. What happens if we consider a convex mirror? A convex mirror. Again, it will have a principal axis which goes through the pole of this mirror, which is the geometrical center of this optical instrument. And again, it will have some focal point here. We say it's negative because it's somewhere behind the mirror. And if we put an object here, we again consider the rays which are convenient for constructing the image. And what rays will be convenient for constructing the image? If we consider the parallel ray, then it will be reflected from the convex mirror in such a way as if it originated from the focus. It will be reflected as if it originated from the focus of this mirror in this way. And also, if we consider the ray which goes into the pole, into the central point, then it will encounter a vertical, small vertical, almost parallel, almost flat area, and it will be reflected from it in such a way that the angle of incidence will equal the angle of reflection. So we will have, for the rays which originate from this point, the upper point of our object, all the rays originating here will be somehow reflected by the mirror. One of the rays will be reflected in this direction, another ray will be reflected in this direction, and so we understand that in the left part of the space, to the left of the mirror, we will have a divergent beam of rays which will all go as if from this point. They will intersect in this point, and so that will be the image of our object. This is the object, and this is the image, H prime. If we look from here, if we put a human eye here, then a human eye will see all the divergent rays as if coming from this point, as if the rays are originating here. So we understand that the rays do not originate in this point, because this point is somewhere behind the mirror, and there is nothing. There may be some material, some solid body, for example, may be placed here, and nothing looking like the object is here. Nothing. But if we put our eye here, we will see the divergent beam of rays reflected by the mirror, and this beam of rays will seem to originate from this point, and we will think that there is an image somewhere behind the mirror. We will see a small virtual image. Virtual, again, this is virtual image because we cannot put here a white screen to observe the image. So this will be a virtual image. Point A prime is the image of point A. A virtual small image of our object formed in the convex spherical mirror. So such are the principles of constructing images in lenses and mirrors. Now I would like to solve some simple problems. Let's consider the first problem, the simplest one. Where should we place an object so that its image in a convex lens be of the same size as the size of the object itself? So we have a convex lens and its principal axis, and there are some focal distances to both sides of the lens, and we have an image somewhere, an object placed somewhere, for example here, and we need to find at what distance from the lens A, we have to place an object so that the image of this object has the same size, the same height. The height of the image h prime equals the height of the object. How to form an image you know very well. If we choose a beam going parallel to the principal axis, then this ray will be deflected to the focal point, and if we choose another beam which goes through the center, it will go undeflected, and at the place where they intersect, where these two beams intersect, there will be an image of point A. That will be the image A prime. If we consider all other points of the object, then we will obtain other images of all the points. So the whole object will have this image, and the height of the image will be h prime. And so if we use the length formula, 1 over A plus 1 over B equals 1 over F, and also we know that here from these two right triangles, this angle alpha and this angle alpha are equal, and therefore the distance b of the image and the height of the image are related in such a way that distance b over h prime equals distance a divided by h. So we have these two equations, and if h prime equals h, then from the second equation we obtain that a must be equal to b. And if we substitute for b a, then we obtain here that 2 over a equals 1 over f. And from here we immediately obtain that a equals 2f. It means that the object must be placed at the distance of double focal distance. A must be equal to 2f. That is, we must have double focal distance, and in this case, and only in this case, the height of the image will be equal to the height of the object. The image and object will have the same size if the object is placed at the distance equal to a double focal distance. Now I would like to consider some more complicated problem. Problem number 697. From Buchovtsev. A thick plate is made of a transparent material whose refraction index changes from n1 on one side on its upper edge to n2 on its lower edge. A beam enters the plate at the angle alpha. So we have some thick plate made of glass. So this is a plate of glass, and the beam enters here at the angle of incidence alpha. And we know that the refraction index here at the upper side equals n1, and then it changes somehow, and here at the lower side, at the opposite side of the plate, the refraction index equals n2. At what angle will the beam leave the plate? So the beam will somehow go here, and it will leave the plate at some angle beta. And we have to find the angle beta if we know only the refraction index on the upper side near the upper surface of this plate, and we know the reflection index near this lower surface. And what happens to this reflection index in between, we don't know. There is some function. The reflection index is some function of coordinate. So if we take a coordinate vertically, a vertical coordinate y, for example, and the reflection index n as a function of y, then we will this graph here at this point, say 0, the reflection index is n2, and then it somehow changes in any way, and at the upper side the reflection index is n1. But what is the change of reflection index in between? We don't know. This is an arbitrary function. So we need to find the angle beta at which the light ray will go out of this glass plate if the light ray falls on the glass plate at the angle of incidence alpha. Let us imagine that this glass plate is divided into small layers, so small that within each layer, the refraction index does not change considerably. It's almost constant. So we will have some reflection index in a previous layer. Let it be layer number k. So this is layer number 1, layer number 2, and then we go as far as necessary and we obtain layer number k, and this is layer number k plus 1. And so here we will have refraction index n sub k, and here we will have refraction index n sub k plus 1. So we imagine that the glass plate is divided into very small, very thin layers of glass. For each interface between the two layers, we can write what? Well, we start from the first layer. If the refraction index here was n0, for example, it was unity, and suppose that the refraction index after the plate here is also equal to n0, also unity. Suppose this is true. Suppose the glass plate is in the air or in vacuum. Then for the first layer we will have that sine of angle of incidence divided by the sine of angle of refraction in the first layer will equal the refraction index in the first layer divided by n0. For the second layer, we will have the sine of angle alpha 1 divided by the sine of angle alpha 2. That is, angle alpha 1 is the angle of light ray inside the first layer, and then in the second layer it will have angle alpha 2, and that will be equal to n2 divided by n1. And so on. We will repeat this Snell's law for each interface between the two adjacent layers. And finally, somewhere for layer number k, we will have, or for layer number n plus k, we will have, for this interface between these two layers, k and n plus k, we will have that sine of angle of incidence from layer k to the layer, to the sine of angle of refraction in the layer k plus 1 will be equal n k plus 1 divided by nk, and so on until the last interface, until the last surface. So we have divided the glass plate into small, very thin layers, and for each two layers we use the Snell's law. Now if we add all these equations together, no, don't add, we multiply these equations. So we multiply the first equation by the second equation. What will happen? If we multiply these two equations, we will see that sine alpha remains here, but sine alpha 1 and sine alpha 1 will cancel. And what we obtain here will be sine alpha 2 equal to what? n1 and n1 here, one in numerator, another in denominator, will cancel, and we'll have n2 divided by n0. And if we go on multiplying by other equations, we will see that each time the sine of alpha in denominator will cancel with the sine of alpha which stands in the numerator of the next equation. And after multiplying all these equations, we will obtain that sine of alpha, the original angle of incidence, divided by the sine of beta, the final angle of refraction, will be equal to n2 divided by n1. sorry, n2 divided by n0. N2 divided by n0. No, that was correct. N2 divided by n1. That was correct. So if we have a refraction index of a glass plate which is varying along the thickness along through this glass plate, so that at one surface the refraction index is n1 and at another surface the refraction index is n2, then we have to use the Snell's law many times for each small thin layer, simple Snell's law, and then multiply all these equations, and then all the intermediate layers, all the refraction indices in between, in somewhere in the bulk of this plate will cancel, and what remains only what we have. No, something's wrong here. Something's wrong. Certainly, something's wrong, because n2 will cancel and n1 will cancel actually, and finally we will have, yes, finally what we will have, it was not very good to suppose that the refraction index in the beginning was the same as the refraction index in the end. Let us suppose that these two refraction indexes are different. So this is NA, for example, and this is NB. The refraction indices at the upper side of the plate and the refraction index at the lower side of the plate. So if we multiply all these equations, then NA will remain here and NB will come here. So that will be defined only by the refraction indices. If we have the same medium here, the same medium, if it's the same medium, then these two indices will be the same. Well, I wonder if we have any more time. Probably we have no more time to consider any more problems. So on this point, let me remind you that this was the last lecture in the course of Introduction to Physics, and the course of Introduction to Physics cannot be considered as a comprehensive course of a secondary school physics. Certainly not. It's just a discussion of some selected topics. But this discussion of selected topics allowed you to understand what should be the level of knowledge of a student so that you could be successful in your further studies. Also, we considered some problems, and this course of Introduction to Physics now allows you to be aware of the level of skills that you must possess in solving problems, so that you could be successful in your further studies in MIPT. So if you know the required level of knowledge and the required level of the skills in solving problems, well, you can assess your own skills and your own knowledge, and you can assess your own chances and your possibilities to be successful. I am absolutely sure that any one of you can be successful if you apply necessary efforts and spend necessary time to study physics. So on this point, let me finish this course of Introduction to Physics lectures, and I wish you a happy new year and see you next semester. Goodbye till then.